This week's theme is the view from home, and it's how the night sky appears from Earth through the course of a year or maybe a night. But for this, we're going to look at something that happens in the night sky over thousands of years. And we'll have to realize that we're not going to see the effects of this in our lifetimes unless we're doing something with an extremely powerful telescope. We'd never notice it with the naked eye. But it's something called precession, and it's been noticed for thousands of years. It's just that we don't tend to be aware of it during a single lifetime. Here's a view, kind of a sky chart view of the northern sky. And you see some lines that are converging at a point there. That point that the lines are converging on is the North Celestial Pole. And it's a point in the sky that would be directly above the geographic North Pole of the Earth. The Earth's rotational axis pokes through that particular point. The star that's very near there, the end of the handle of something, that little something happens to be the Little Dipper. But Polaris is the star that's there right now, and this is as of 2020. Hasn't always been that way. In 3000 BC, which would have been about 5,000 years ago, a little bit over that, at that time the Sumerians had developed pictograph writing and used wheeled transportation, but at that time the nearest thing to a North Star was the star Thuban in Draco. Now, people at that time made note of this. They saw that during the course of a night, all of the stars in the northern sky appeared to wheel around this point in the sky that was near Thuban, and including Polaris at that time. Polaris would have completed a fairly large circle around that point Thuban. 2000 BC, Stonehenge was under construction. The 11th dynasty in Egypt. I actually know nothing about Egyptian history except that they did domesticate the cat to kill snakes. But the North Celestial Pole, had moved a little ways past the star Thuban, and it was heading in the direction of Ursa Minor, the Little Dipper there. But it had moved. And people even at that time would have noticed this. 1000 BC. It isn't particularly close to any bright stars, although the star Kokab in Ursa Minor is nearly as bright as Polaris, and it would have been a half-decent northern star at that time. But that was 1000 BC. David was the king of Israel. There were irrigation canals in Tucson, Arizona. Not by European settlers, though. Alphabets were developed, and the Chinese had kites that could carry people. I don't think I would have wanted to have been in one of those things. Okay, about the time of the birth of Christ, let's see, the North Celestial Pole was nearest Kokab at that time, a little bit farther away from Polaris, and so Kokab probably would have been the North Star at that time. All of the stars in the sky would wheel around that point in a night. 1000 AD. By now, the Polaris is starting to be probably the best North Star at that point, and so you could have used it for finding your way at night. By the way, in all of the times we've been talking about here, they would have been dark skies that you would have enjoyed. There would not have been any electric lights on all night. It would be a rare night when, well, if you had clouds you couldn't see anything, but it would be a rare night when you couldn't see a lot of stars. And people would have been much more aware of the sky at that time than they are now. Okay, so 2000 AD, we've got Polaris as our North Star. But it's something that's going to continue to change. And in 3000 AD, Polaris will be farther away from the North Star at that point, although it'll still be the brightest star anywhere near it. That star Eris, I'm guessing that's how you pronounce it, in Cepheus, is not particularly bright. Polaris isn't a super bright star either, but it's brighter than any of the stars there in Cepheus. By 4000 AD, definitely Eris, however you say it, will be the North Star at that time. And then the North Celestial Pole will continue to work its way into Cepheus, which is not a particularly bright constellation, so nothing particularly important in there. 10,000 AD, which is as far as my software would go, the North Star at that point will probably be Deneb, which is actually a brighter star than Polaris to our eyes, and so it'll be okay. In about 6,000 years after this, the North Star will be, or the North Celestial Pole will be very near to the star Vega, which is straight up from the North Celestial Pole in this picture, almost straight up. And it's a quite bright star. It's one of the brightest stars in the sky. So we'll have a pretty good North Star at that time. So it's been moving through the sky. And an interesting thing is, by about, maybe 100 BC or something like that, a Greek astronomer had calculated the speed at which the North Celestial Pole was moving through the sky. They didn't call it the North Celestial Pole at that time. I'm not sure just what name they had for it. But they'd noticed this for thousands of years, just based on verbal records for the most part, or oral records, although they did have scrolls written down of things. But they'd noticed it and calculated how fast it was moving. Okay, this is a star chart that I had a link for you to print this off if you want to. And where all those lines converge at the center of this right now is where Polaris is. That's the North Celestial Pole. But there's a circle on this that I'll try to trace out with my mouse pointer, and I'll try to go slow so you can follow it, but it's this dashed line here. And if you read carefully the words there, it says the orbit of precession of the pole. And so that's the path in the sky that the North Celestial Pole is following. And so that's what's going on with the motion of that thing. Yeah, it gets fairly close to Vega. Certainly not as close as it is to Polaris right now. Polaris is within about 7/10 of a degree of the North Celestial Pole right now. So it's quite close, and that's probably about as close as any reasonably bright star will ever get to it. So that's what precession happens to be. It's a slow circular motion of the North Celestial Pole through the stars. And it takes about 26,000 years for that path to be followed out. So it's definitely not going to be noticed in a human lifetime. A human lifetime, even if you estimate it as 100 years, is only, let's see, that is 1/260th of 26,000 years. And so it might move a degree in an entire human lifetime, but that's not very far along that circular path. And so just isn't going to be noticed in a human lifetime by naked eye observations. It takes generations for that thing to show up. Now I want to draw some pictures and show you something about the cause of this effect. It turns out the cause of precession is due to a force that we haven't studied yet in class, but it's the force of gravity. And here's what's going on in this case. I'll try to draw just a couple of circles on here. This is can represent the Earth. And I'll draw a rotational axis for the Earth that hopefully goes right through the center of it. I forgot to mark the center when I was drawing this, but this could be the north rotational axis of the Earth, and this could be the south. So the North Pole would be right here, and the South Pole right there. Now, primarily due to the gravitational effect of the Sun and the Moon, which are actually out in this direction. Let's see, I'll draw the Earth's equator on here anyway, because we want to consider that. But let's just imagine that we have the Sun way over here, and this is not to scale. Remember, if the Sun was a tennis ball sized object, the Earth would be about the size of a period on a piece of paper, about a room's length away, a classroom's length away. But the Sun exerts a gravitational influence on the Earth, and if the Earth was a perfectly round sphere, it wouldn't have much of an effect on it whatsoever. However, the Earth is not a perfectly round sphere. I'm going to have to exaggerate this effect, but the Earth is a little bit fatter at the equator than it is at the poles. And so there's a little bit more mass for the Sun's gravitational force to act on here than there is anywhere else on the Earth. Now, what this would tend to do if the Earth was not rotating is make the Earth's rotational axis go this way until this was lined up with the Sun. But rotating objects behave weirdly, and I'll track down some videos for you to watch about how weird they behave. But what happens instead of the Earth's rotational axis righting itself by going upright like this is that the rotational axis actually sweeps out a cone in the sky very slowly, because it's a very subtle effect. But over a 26,000 year period, that rotational axis sweeps out a circle in the sky because of the gravitational influence of the Sun. The Moon also has an effect on it, more or less the same thing. The Moon and the Sun lie in about the same plane with each other. Sometimes they're on the same side, sometimes opposite. But the Moon also adds to this effect. But between the two of them, they cause this rotational effect that we call precession. And again, the Earth isn't that much wider at the equator. It's mostly spherical, and so it's a very small and slow effect. But over a course of 26,000 years, it does that sweeping motion in the sky. And that's what precession is. And it's the Sun's gravitational influence that causes it. So Isaac Newton, back when he was doing his work, was actually able to calculate what the effect of the precession was. By the time of Newton, it had been well observed for centuries, but people didn't really know what had caused it. Newton could show that it was due to the gravitational influence of the Sun.